Hi everybody. In this video, we're going to talk about vectors. But first, let's talk briefly about numbers. Numbers express magnitude. So, for example, if you want to talk about how big something is or how much of something you have, you would use numbers to express that. Like, I have 5 apples, or that building is 700 feet tall. We would use numbers like that to make those sorts of descriptions. But sometimes we not only want to know how much of something there is, or how powerful it is, or how big it is, we also want to know the direction that it's moving in. And for that, we would use vectors or arrows. Okay, so vectors are just arrows. There are other ways of defining what a vector is, and sometimes the word vector is used slightly differently in different contexts. But for our purposes right now, when we use the word vector, we're just talking about an arrow. So, like numbers, vectors can express magnitude, how powerful something is or how big something is, but vectors can also express direction. So, for instance, a vector might be used to describe the wind. And if the wind is blowing really strong, then we might draw a vector which is very long. Okay, so the length of the arrow, or the length of the vector, tells you the magnitude of that vector, how big it is, how powerful it is, how strong it is. And then the direction of the arrow, or the vector, tells you what direction it's moving in. So, for example, if we have a very strong wind which is blowing diagonally, maybe it's blowing up and to the left, then we would draw a long arrow moving up and to the left. Pretty simple. Or maybe the wind is not blowing very hard. Maybe the wind is only blowing a little bit, and it's blowing completely to the right. In that case, we would draw a smaller arrow. So the length of the arrow, which indicates its magnitude, would be shorter, and it would be moving to the right. Okay, so arrows or vectors are used to express both magnitude and direction. All right, so let's move on. Vectors with the same magnitude and direction are considered to be the same even if they are in different places. So let me just take this vector and copy it, and then put it anywhere. I could put it over here. Okay. This vector and this vector are both the same vector. Even though this one is over here and this one is over here, the magnitude of both of these vectors is the same. They're both the same length. And the direction of both of these vectors is the same. They're both pointing in exactly the same direction. So these vectors, even though they're in different places, would be considered to be the same vector. Even if I were to take this vector and put it over here, they're still the same because the magnitudes, the lengths, are still the same, and they're still pointing in the same direction. Okay? So moving on, the ends of a vector are called the tail, where the vector begins, and the head, where the vector ends. So let's just draw that. So this right over here would be the tail of this vector, and this would be the head of this vector. Okay? And this would be the tail of this vector, and this would be the head of that vector. Okay, so pretty simple. The tail is where it begins, and the head is where it ends. Okay, now let's talk about operations. Every time you learn about a new type of thing in math, like negative numbers or complex numbers or logarithms or now vectors, anytime you learn about something different, then you want to know, okay, what happens when you add them? What happens when you subtract them? All that good stuff. So we're going to talk about addition now. How do we add vectors? The operation of addition is defined by attaching the tail of one vector to the head of the other, then drawing a third vector from the unconnected tail to the unconnected head. All right, so let's take the tail of this vector and attach it to the head of this vector. Okay. All right, so just like that, I connected the tail of this vector to the head of this vector. Then we're going to draw a third vector from the unconnected tail. So this tail is unconnected to the unconnected head. This head over here is unconnected. So let's draw a third vector from here to here. And I'm gonna draw it in green. I'm gonna just change that to green. In this video, I'm gonna have the sums, or sometimes the differences written in green, drawn in green. Okay, so this vector over here is considered to be the sum of these two vectors. All right, so that's how you add vectors together. And addition is commutative, which means we could change the order. So remember, we put the tail of this vector onto the head of this vector. But if we had done it the other way around, if, let's say, we put the tail of this vector, okay, so the tail of this vector onto the head of this vector, and then, again, we draw, for the sum, we draw another vector from this unconnected tail to this unconnected head. You can see that this sum vector is exactly the same as this one over here. Okay, same magnitude, same direction. So addition is commutative with vectors, just like it's commutative with regular numbers. Like 5 plus 3 is 8. 3 plus 5 is also 8. You can change the order and still get the same answer. Here, you can. It doesn't matter which tail you connect to which head, you'll still get the same answer. So addition is still commutative with vectors. We can express all of that algebraically by saying that a vector A plus a vector B, or adding B to A, is the same thing as vector B plus vector A, or adding vector A to vector B. When we use these little arrows above these letters like this, it just means that what we're talking about is a vector rather than just some number. So let's call this vector vector A, and this vector vector B. So here we have, again, vector A. I just copy and pasted this and put it over here. And here we have vector B, which means that this vector over here is the vector A plus B. Okay? But we could also do B plus A by starting with this vector, and that's what I did over here. So this is vector B. This is, over here, vector A. And this would then be the vector B plus A. But just like we saw a couple minutes ago, these two vectors are exactly the same. They have the same magnitude and they have the same direction. Okay, so again, that's the commutative property. The order doesn't matter. All we've done here is we expressed it more algebraically by naming them A and B and writing a little equation over here. But it's the same thing that we were just talking about. All right, so moving on. To multiply a vector by a scalar, which is just a number, just a regular number, make the vector that many times longer. If the scalar is negative, point the vector in the opposite direction. Okay, so let's just go back to our, let's stick with these vectors over here. Let's call this vector, A. Okay, just a little notation. When you're talking about vectors and you want to name them, very often people will put a little arrow above the letter just to indicate that A is a vector. A is not just a plain number. Okay, so if I call this vector A, and then I want to multiply it, let's say by 2, what does that mean? Well, all that means is I'm simply making this vector twice as long. So if this is vector A, then vector 2A would look something like this. I'm just going to do it freehand so I won't get it perfectly. But it would be moving in the same direction, and it would be twice as long. If we wanted the vector If we wanted the vector 3A, then that would be 3 times as long. All right, again, I'll just do it freehand. So 1, 2, 3, about that. Okay, so this would be the vector 3A. Okay, fairly simple. What if we wanted to do, instead of positive 3A, what if we wanted to do negative 3A? That just means that the vector would be pointing in the opposite direction. So it would be 3 times as long, but in the opposite direction. So instead of looking like this, it would, whoops. It would look like this. 1, 2, 3. Ugh, that was not very good, but hopefully you get the idea. Okay, 3 times as long, but moving in the opposite direction. Let's call this vector B. What if I wanted the vector negative B? What would that look like? Well, that's like negative 1 times vector B. So I'm not changing how long it is. So making something 1 time as long means we're not changing the length at all, but it would be moving in the opposite direction. So if this over here is vector B, then we could just make that go in the opposite direction. This would be vector negative B, or negative 1B. All right. Now, also keep in mind that what we've done here is we've done a few examples where we're multiplying a vector by a scalar. That's what we've done. We are not going to be talking about in this video multiplying 2 vectors together. Okay, we just did a vector times a number. Okay, that's what we just did. We did not talk about multiplying 2 vectors together, and we're not going to talk about that in this video. I'm just mentioning it to you so you can so you have the mental distinction in your head that that's not what we did. Okay, there are actually a couple of different ways of multiplying 2 vectors together. There would be what's called a dot product and what's called a cross product. We're not going to talk about that in this video. In this video, as far as multiplication goes, we're just going to talk about taking a vector and multiplying it by a number, not 2 vectors multiplied together. Okay, so now let's move on. The letter I is used to refer to an arrow that is 1 unit long and pointing to the right. So let's say that the magnitude of this arrow is 1. Okay, magnitude being how long the arrow is. So we're saying that this arrow, or this vector, is 1 unit long and it's pointing to the right. We call this vector vector I. Don't get that confused if you're a little bit familiar with complex numbers. Sometimes the letter I is used to mean the square root of -1. That's a completely different context. The letter I is also used when you're talking about vectors to indicate a vector that has a magnitude of 1 and is pointing to the right. It's pointing in the positive x direction. If you think of an x-axis and a y-axis, then the vector I has a magnitude of 1 and it's pointing in the positive x direction. Okay, and the letter J is used to refer to an arrow that is 1 unit long and pointing up. So this vector would be called vector J, okay, as long as the magnitude is just 1, so it's 1 unit long, and it's pointing in the positive y direction. Okay, so that's vector I and that's vector J. And we can write a vector, any vector, in component form by describing how the vector can be made from i's and j's. So let's take a look at these vectors over here. We can describe these qualitatively by saying, okay, this one is kind of a medium length and it's pointing up and to the right. This one is also about medium length, it's pointing up and to the right. This one is longer and it's pointing straight down. We can describe vectors qualitatively like that just by using our words. But if we want a more quantitative description, then we would put them in component form, which just means break them down into i's and j's. So let's take a look at these three vectors over here, which I have drawn again down here. Okay, you can see that I just took these three blue vectors and copy and pasted them so that they're now over here. But now it's easier for us to see how to describe them in component form. So this vector over here, we can see is made from 3 of the I arrows and 1 of the J arrows. So we could say that this arrow, you know what, let me switch to blue, since really I'm talking about this arrow, but I could say that that is 3i plus 1j. And in fact, you don't even, if the coefficient here is just 1, you don't even have to write it. So we could just write that as 3i plus j. There is another notation. We could use these, what are called angle brackets, and say that this vector is 3, 1. Okay, where this first space is how many i's you have, and then the second space is how many j's you have. It's very similar to writing coordinates on a coordinate plane. Let's move on to the second vector. How would we write this one in component form? Well, since these horizontal vectors are pointing to the left, we would, and there are 2 of them, we would start by writing negative 2i and then plus 2j. Actually, it is also okay if you want to write 2j plus negative 2i or 2j minus 2i. That would also be fine. Using this angle bracket notation, it would be negative 2, 2. By the way, when I use the word notation, I'm just talking about how we write things. So there are different ways of writing this. Okay, now let's do this third vector over here. The breakdown for this vector is that there are no horizontal vectors at all, and the vertical vectors are pointing downwards. So this would simply be negative 4j. We can see that we have 4 vertical vectors pointing down, no horizontal vectors. Using the angle bracket notation, it would be 0, negative 4. Okay, I do want to talk a little bit more about why this first notation makes sense by writing 3i plus j. It makes sense based on what we talked about earlier in the video. So first of all, if we have the vector 3i means take an I vector, which looks like this, remember, and make it 3 times longer. Okay, I actually drew 3i vectors, but 3i literally means take an I vector and make it 3 times longer. It would look like that. And then if we add a j vector to that, remember what adding vectors together means. It means we would take the tail of the j vector and attach it to the head of the I vector, of the 3i vector, and then draw a third vector from the unconnected tail to the unconnected head. So hopefully now it does make a little bit more sense why this vector over here is called 3i plus j. It does follow from what we were talking about earlier about multiplying a vector by a scalar and also adding 2 vectors together. Okay, and the same thing can be said for all of these over here. Negative 2i means we take our I vector, and then since it's negative, we would make it go in the opposite direction. And then since we're multiplying by negative 2, we would make it twice as long. I'll just draw it over here now. Okay, so that would be our vector negative 2i. This vector over here would be 2j. If this is j, then this would be 2j. And then adding these 2 vectors together, meaning connecting them tail to head, and then drawing a third vector from here to here, from the unconnected tail to the unconnected head, that would be the sum of these 2 vectors. So hopefully that makes this notation makes a little bit more sense, because we are, even though these are 2 different vectors, when we write this whole expression, we are just talking about one vector. We're talking about the vector over here. And so it might look a little bit strange to talk about one thing using 2 terms like this, but hopefully it makes sense to understand that this vector really is the sum of these 2 vectors over here. All right, so let's move on. Vectors can also be added by adding their components. So we did talk about how to add vectors together by connecting them head to tail and then drawing a third vector. But if we know the components of the vectors, meaning we know how both vectors can be broken down into i's and j's, then we can simply add the components of those 2 vectors together to add the vectors together. All right, so let me show you what I mean by that. Okay, so here I have a vector 2i plus j, or using the angle bracket notation 2, 1, and I want to add this vector together with this vector, and this vector is 3i plus 3j, or in the angle bracket notation 3, 3. Okay, what would the result be if I added this vector and this vector together? Well, let me first go back to the first way that we learned about, which is just to connect them head to tail and then draw a third vector. So let me copy this one and put it over here. And then I will copy this one and put it over here. All right, so the sum vector would be from here to here. Let's make that a little thicker so you can see it better. All right, so this green vector over here would be the sum of these two vectors. So we just added it using this strategy. But if we know the components of the vectors, then we could have also simply added them component by component. So if we know that this vector is made from two I vectors and this vector has three I vectors in it, then the sum vector should have 2 plus 3 or 5 I vectors in it. And you can see that it does. 1, 2, 3, 4, 5 I vectors, just like that. Okay, and if this first vector has 1 j vector, and this second vector has 3 j vectors, then when we add them together, the third vector would have 4 j vectors. So the coefficient here is 1, even though it hasn't been written. And 1 plus 3 is equal to 4. And hopefully this diagram over here helps you understand intuitively why that's true. So you had the 2 I vectors from this first vector, plus the 3 I vectors from this second vector, makes 5 I vectors altogether. Then you had the 1 j vector from this first vector, and then you had the 3 other j vectors from this second vector. So then 1 plus 3 is 4. So this sum vector over here is 5i plus 4j, okay? Let me go back to this heading over here. All right, and that would work also if we had some negative numbers. So let's do an example with a couple of negatives thrown in there. So this vector is no longer 2i plus j. Now it's negative 2i plus j. Notice that these horizontal vectors are now moving to the left. We want to add that to this vector over here, which is 3i plus negative 3j. Notice that these vertical vectors are moving down, which is why we have this negative 3 in front of the j instead of positive 3. Okay, what would the result of that be? Well, we could simply add them component-wise, and then I'm going to add them the other way, and you can see that we get the same answer. So the coefficient in front of the I is negative 2. The coefficient for this vector, and the coefficient in front of the I for this vector is 3. So I'll just do it on the side over here. Negative 2 plus 3 is positive 1. Okay, so we end up with just positive 1i. I didn't even write the positive 1 in front of the I here, but you can write it in if you want. And then for the j, look at the coefficients in front of the j's. The coefficient in front of this j is 1. You can see I did write it over here in the angle bracket notation. The coefficient in front of this j is negative 3. So if we do 1 plus negative 3, that's the same thing as 1 minus 3, which is negative 2. So the coefficient in front of the j for the sum vector should be negative 2. So the final answer is I plus negative 2j. You could also write that as I'll do it in green. You could also write that as I minus 2j. If you wanted to, you could write it as negative 2j plus I. That would also work. Okay, so you can write it in different ways. But let's see where this came from. So we can see that there is one I vector, and there are negative 2j vectors, meaning 2j vectors but pointing down instead of up. Okay, we can see that the final sum vector will have these components. But why? So let's talk about why now. If we take this first vector, position it over here, and then we connect the tail of this second vector to the head of the first vector. Right? You can see, maybe I didn't do that perfectly, but hopefully you get the idea there. Then we draw a third vector, which is our sum vector, from this unconnected tail to this unconnected head over here. You can see that this sum vector does match the components which we already had, 1i vector and then negative 2j over here. So why did that happen? Well, we had two horizontal vectors moving to the left for this arrow. So it's like we went 2 spaces this way, but then 3i vectors moving to the right for this arrow. So from here, then we went 3 spaces back to the right, 1, 2, 3. We ended up with just one horizontal arrow in the pointing toward the right. And then now let's talk about the vertical components. For this vector over here, we had just one j vector pointing up. Okay, so imagine going 1 space up. But then for this vector, we had 3 vertical vectors going down. So from here, imagine going down by 3, 1, 2, 3. You can see why we end up with these 2 vertical vectors moving down over there. Okay, so hopefully it makes sense why you can just add the components in order to add the vectors. Okay, the components being the coefficients that are in front of the i's and the j's. All right, let's move on now and talk about subtracting vectors. So far, everything that we've been doing was addition. Even though we had some negative numbers in there, really we have just been doing addition. Now let's define what subtraction is. To subtract vectors, multiply the vector you're subtracting by -1 and then add it to the other vector. Oops. Okay, so let's take, for example here, another a and b vector. And let's say we wanted to do a minus b. What would that mean? What do we mean by that? It means that we're taking vector A. I'm just going to copy and paste it and put it over here. Okay, we're putting that somewhere. And then before we add b to it, we have to multiply b by -1. What does that mean, to multiply b by -1? That means we keep the length the same. We're going to keep the magnitude the same, but we're going to make it go in the opposite direction. Okay, so you can see here, this vector is now moving in the opposite direction as this b vector. Okay, so this is the vector A. Oops. This is the vector A. This is the vector -b. And then the sum vector would be a minus b. Okay, this vector over here, which we got by adding these two vectors together, is what we mean when we say a minus b. Okay, and this is all very similar to regular numbers. So for example, you know that 5 minus 2 is the same thing as 5 plus -2, right? So it's very similar to what you're already used to with numbers. All right, so subtract. So just to reiterate, subtracting means you take the number that you're subtracting, you make it go in the opposite direction, or which is multiplying it by -1, and then you add it to the first vector. Okay, moving on. Okay, just another little analogy with regular numbers. Just like 7 minus 2 equals 5 implies that 5 plus 2 is equal to 7. So maybe you remember from elementary school when you did addition and subtraction families. And your teacher said, okay, if you know that 7 minus 2 is equal to 5, then write an addition sentence using those numbers. And then you would rearrange them and you say, okay, so if I know that 7 minus 2 is 5, then that means that 5 plus 2 should be equal to 7. Well, we can say something similar for vectors. If we know that A minus B is equal to C, okay, so let's just name this. I know that this is A minus B, but let me just rename that. I'm just going to call it C. So if I know that vector A minus vector B is equal to vector C, then it should also be true that vector C plus vector B is equal to vector A. Let's see if that actually is true. Let me keep vector C here. And this is telling me to add vector B to vector C. So let's do that. Okay, and then I'll do the sum this time in pink. This over here would be the vector C plus B. Okay, drawing another vector from the unconnected tail here to the unconnected head here. Okay, but you can see that this vector C plus B is exactly equal to vector A. Maybe I didn't draw it perfectly because I'm doing it freehand, but hopefully it's close enough that you can see that these really should be exactly the same. So it works very similar to numbers. If I know that 7 minus 2 is 5, then I also know that 5 plus 2 is 7. Well, if I know that vector A minus vector B is C, then I also know that vector C plus vector B is equal to vector A. All right? Moving on. To find the components of a vector. Oh, actually, I forgot something. Whoops. Let's continue. Oopsie. Okay, let's go back to here. My bad. I wanted to talk about this before the other one, but it doesn't matter. To subtract. Okay, so we're going back to subtraction, which is like taking the second vector, making it go in the opposite direction, and then adding it to the first vector. We already talked about that, but now let's just do it with components, okay? So if I want to do the vector 2i plus j minus the vector 3i plus 3j, that's the same thing as multiplying this vector by -1 and then adding it to this vector. And we can do that component by component. All right, so -1 times all this would be -3i minus 3j. Okay, and then if we do 2 plus -3, I'm going to write that over here. 2 plus -3 is equal to -1. Okay, you can see over here I wrote -i, which is the same thing as -1i. And then here I'll just write in the 1. 1j plus -3j Let's just add the coefficients. So 1 plus -3 is like 1 minus 3, which is -2. And you can see over here we have minus 2j. Okay? So remember that if we want to subtract, if we have to, let's pretend that this wasn't there for a second. If I had these two vectors and I wanted to subtract them, then what I would need to do is change the sign of both of these by multiplying this by -1, and then I could add the components together. Okay? And let's just see that what we just did follows what we said before, where we're taking, if I want to do a minus b, then I'm taking a, and then before I add b to it, I would change the direction that b is pointing in, then connect it head to tail. Okay, and you can see that the results, this sum vector over here would have components -I minus 2j. Okay? All right. Good, and we already talked about this, a little bit out of order. Now let's go to the next thing. All right. To find the components of a vector when the endpoints are known. By the endpoints, we just mean where the head and tail are. Subtract the coordinates of the tail from the coordinates of the head. Okay, so if I wanted to know what the components of this vector are, then how could I do that? Well, if I have it printed on a coordinate grid here, and I know the coordinates of the head and I know the coordinates of the tail, I can simply subtract the coordinates of the tail from the coordinates of the head. Okay, so for instance, if I know that the head here is at 6, -1, and I know the tail is at -3, 5, okay, -3 on the x-axis, 5 on the y-axis. Notice I'm using the curved parentheses here. So I'm just talking about the coordinates on a coordinate plane, like you've been doing for a few years already. I'm not using the angle brackets, so I'm not actually talking about any vectors here, just the coordinates of where the endpoints are. Okay, but if I did want to find the components of this vector, I could simply subtract the components of the tail from the components of the head, which means I'm doing the components of the head minus the components of the tail. Okay, so let's start with the x values, which are going to give us the coefficient for I. We would do 6 minus 5, which is 1. And then for, oh, I'm sorry, whoops, whoa. Not minus 5. Okay, so you can see I just made a mistake. Okay, we actually want to do this one minus this one. My bad. So we're not doing 6 minus 5. We're doing 6 minus -3, which is the same thing as 6 plus 3, which is 9. Okay, that makes more sense. And you can see here that if we drew some I vectors in here, there should be 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's go ahead and subtract the y values. So I want to do this one minus this one. So -1 minus 5 is equal to -6. Okay, and you can see that we do have the opposite of 6j vector. So a j vector is supposed to go up, but you can see that these vectors, which I'm going to draw, are going down, and we do have 6 of them. 1, 2, 3, 4, 5, 6. So the components of this vector are 9, -6, using the angle bracket notation, or we could also write that as 9i plus negative 6j, or we could write it 9i minus 6j. Okay, all of these really mean the same thing. All right, let's move on to the last thing we're going to talk about in this video, which is magnitude again. So how do we calculate the magnitude if we know what the components are? So the magnitude of a vector can be found by using the formula: the magnitude of A is equal to the square root of the x component of A squared plus the y component of A squared. And really, this is just the Pythagorean theorem. So first of all, I need to explain some notation. These two lines here just mean that we're talking about the magnitude of vector A. In other words, we want to know how long vector A is. That's what our goal is by using this formula. To get that, we're going to take the square root of the x component squared plus the y component squared. So A sub x just means the x component of vector A. That's just the coefficient that we were putting in front of I. And the y component of vector A just means the coefficient that we were putting in front of j. All right, this will all make a lot more sense if we do an example, so let's just do one. So this vector would be 4i plus 3j. Okay, and let's just call this let's call this vector A. So if I wanted to know the magnitude, okay, draw those two lines to indicate magnitude. If I wanted to know the magnitude of vector A, which means how long it is, the way that I would figure that out is by taking the square root of the x component squared, which is just the coefficient in front of I, plus the y component squared, the y component being just the coefficient in front of j. Okay, so this is going to give me the square root of 16 plus 9. 4 squared is 16, 3 squared is 9. 16 plus 9 is 25. So we have the square root of 25, which is 5. Okay, so this vector is 5 units long. That's what we just figured out. If this is 4 units long and this is 3 units long, then this is 5 units long from here to here. Okay, now this might look kind of similar to you, and it should, because really we're just doing the Pythagorean theorem. If I have a right triangle which has legs which are 4 units and 3 units long, and I want to find the hypotenuse of that right triangle, how would I do that? I could write the Pythagorean theorem: a squared plus b squared equals c squared. I can plug in the legs for a and b. I would get 4 squared plus 3 squared equals c squared. Okay, and by c here, we're really just talking about the magnitude of vector A. Okay, and then this would give me 16 plus 9, which is 25. And then c would be the square root of 25. Okay, so this is just a quick way of getting what you need to get from the Pythagorean theorem. Okay, in the end, you could use the Pythagorean theorem to do this, but instead of writing this all out, you could sort of just take a shortcut and take the square root of the x value squared plus the y value squared, and that'll give you the final answer. Whoops, so c is equal to 5. Okay, let's just do another example just to show you that this works even when the components are negative. So in this case, this vector would be negative 4i, since these arrows are moving to the left, and then minus 3j, since these arrows are moving down. And then if I wanted to find, let's call this a again. If I wanted to find the magnitude of vector a, then I would do the square root of negative 4 squared plus negative 3 squared. But negative 4 squared means negative 4 times negative 4, which is still positive 16. And negative 3 squared means negative 3 times negative 3, which is still positive 9. So I'm just going to get the same thing that I got before, because the magnitudes of these vectors over here were the same. It didn't matter that they were moving to the left and down instead of to the right and up, because when you square a negative number, you just get a positive anyway. So it's okay to put negative numbers into this formula over here. It still works, okay? All right, so I'm going to end the video there, and have a great day.